second order expansion, Taylor expansion of f, and it's minimizing that second order expansion, right? So Taylor's theorem says that, if you look at f of x1, well, let's say f of y, just some f of y, approximately up to some error that comes out of Taylor's theorem, this is equal to f of x0 plus the gradient of f at x0 dotted with y minus x0 plus 1/2 y minus x0 dotted with the Hessian of y minus x0. Okay. So this is what Taylor's theorem says in terms of approximating f by its second order expansion. And Newton's method is basically just assuming that this is an equality and then just tries to minimize the right-hand side. Okay? And the minimum of this right-hand side is exactly this if you do calculus. All right, so we just need to understand how well Newton's method does. So are there any questions so far? Okay. So let me write down a theorem. So again, for t in 0, 1, define xt to be x0 plus t times x1 minus x0, where by x1 I mean that x1, and by x0 I mean our the point that we're currently at. Suppose there exists an epsilon, a positive epsilon, such that for all t in the interval from 0 to 1, we have that the following is true. 1 minus epsilon times the Hessian of f at x0 is at most in the loner ordering. The Hessian at xt is at most in the loner ordering 1 plus epsilon, the Hessian at x0. I suppose that that's true. So remember, when we were analyzing gradient descent, it was a first order method. We only had access to the gradient. We couldn't actually compute the Hessian, but we had a promise about the Hessian, right? We were told that the Hessian is well conditioned. Okay, there's some small gap between its largest and smallest singular values. So again, for Newton's method, we need to have some kind of promise to say that Newton's method does well. Okay, and the promise that we're going to make use of is that the Hessian doesn't change too much on the line that connects x0 to the next iterate. Okay? Just to recap, when I say that a matrix A is at most a matrix B, remember that means B minus A is positive semi-definite. So suppose that's true, then I want to measure progress. And the way that I'm going to measure progress is that, okay, so is to say this. So the norm of the gradient of f at x1 under this, I'll say what this means in a second. Okay. So this is our progress theorem. Okay. So just a definition to make sense of the progress theorem. for a positive semi-definite matrix A, when I say the norm x sub A, that means, by definition, what I mean is x transpose AX square root. Okay. So we'll get into where this is going to why this is going to be useful for us in interior point in a second, but ignore this thing over here. It's telling us that the norm is changing, okay, but the norm isn't changing too much because these matrices are very similar all across the line. In particular, the Hessian at x1 is very similar to the Hessian at x0. So pretend for a second that these are the same matrix. Okay. So in other words, these are the same norm. It's telling us that our new norm of the gradient is at most the old norm of the gradient times roughly epsilon. Okay. And the minimizer is when the gradient is 0, right? So we're getting closer to having 0 gradient. So that's how you should interpret this. Okay. Are there questions before I actually prove this? Okay. So let me give you a proof. I should confess I'm not an optimization expert, so I don't know the proper citation for this proof, but this is a proof that, anyway, Aaron Sidford was kind enough to share with me, so I'm just going to show you this proof.